Great. Yeah, thank you for the introduction. On my title screen, you can see another usage of digital twins. In this case, we try to support a development process of a test bed because it's a relatively complex one. And I have structured my presentation in 4 parts. First of all, I will give you motivation why we are interested in this kind of test bed. Second, I will explain our research approach. Then I will continue with a short case study, and then I will give you a summary and a short outlook. Okay, we are working in the building industry, in the building sector, and there are some interesting emerging VR, AR applications. For example, you can do building design with virtual reality models to discuss this in a group. Second, you can go on the urban planning level, also with VR models to discuss a good design of or improvement of city quarters. Then you can visit today, for example, with Google Earth VR, the entire world. The majority of the large cities are modeled in 3D. And we have also more application for VR and AR on the building side, where you can control the progress of the building process on the building side. Okay, this is one ongoing development in these fields. Then, induced by the gaming industry, we have some interesting approaches where we get physical feedback for our body. For example, the nice project from Switzerland, Berkeley, where you can fly like a bird over space, or if you are cycling on a home trainer in connection with Google Street View, you can feel the inclination. For example, if you are cycling up a hill and then you have a change in the force feedback on your home trainer. Then more in our field, we have some interesting developments more from the professional side, something a little bit from the gaming industry. We have the gloves and sleeves of Thermal Real Plus, where you can feel very dynamic, for example, the cold of a snowball on your forehead. Then we have something for our face, for example, the development of Feel Real, where we can feel heat and cold on our skin. And then we have the full body experience, for example, from the Tesla suit, where we can feel different actuators distributed of our inner skin surface, and then we can have the sensation of heat and cold on the entire body. Okay, what is the present situation in building energy simulation? Typically, we are sitting in front of a computer using tools like Energy Plus or either ICE or also Modelica libraries in combination with Modelica tools. And finally, we get a nice curve for example, for the temperature. This is nice, very professional, but there are some missing features. We have no immersive experience for the user. We are disconnected to the space model. We could improve this by taking the user into a virtual world. Then he or she is embedded in the VR environment. Second, we have no interaction with the model doing simulation. The typical workflow is simulate, waiting, getting results, adapt parameters, then go back to one. Also, this could be more interesting if we would have the possibility for a real-time interaction for the users. This is possible with in the virtual world, and we have to connect it with the simulation models. Third, we have no climate experience of the simulated values as a pure intellectual experience. We cannot feel really temperature diagrams, but what we could do, we could embed the user in an experiential climate space, then he or she can feel or experience something. Okay, starting from this motivation, we come to our research approach. First of all, we created an experiential thermal display where you can have boundary conditions of temperature, moisture, or radiation. Second, we have a Modelica model which simulates the building states of the indoor climate and combine it with Unity framework from the gaming industry. So we have the interactive virtual room for the user within Unity, and we have the physical calculation of the model states in Modelica. Finally, we assembled all this stuff together to a test bed, which integrates some sensors, the Unity model, the Modelica model, and also a control system, openHAB, which interconnects the different parts of the test bed. Okay, then to realize a complex system like that, we come to a lot of open design questions. This is the motivation for the digital twin, which we need before we build the real test bed. For example, vary the size or the shape of the climate chamber, because the inertia, it will definitely different if we have a larger or a smaller space. It's a very crucial question. Second, we have to select different devices which can simulate or reproduce the climate within the climate chamber. The best combination and the capacity of the different devices, what is a maximum reachable system dynamics, because we are interested in dynamic simulation. Then we want to evaluate the control algorithms. What could be a higher level algorithms for all the devices which are used for this climate chamber. And finally, we are interested in different simulation scenarios. We are beginning with a simple, stupid single room, but then we want to become more complex. What is going on if the user is changing one room to the other room? What does it mean for the dynamic, for the needed dynamic of the system? Okay, so I come now to the point where we are using the digital twin. In the first case, without having the real test bed, you can see here our tool chain. We have Unity. Unity is connected with a Modelica thermal model. We have our control strategy in openHAB. And finally, we have a digital twin of the real non-existent test bed. And then we can substitute, if we have gained knowledge from the digital twin by the real test bed, but now the user is sitting within a real virtual environment, and the rest of the system, the control strategy and the thermal room model is still the same. Okay, now I want to explain the digital twin model a little bit more in detail. You can see here in the lower part of the Modelica model, you can see the digital twin model. In the center, the thermal dome surrounded by some air conditioning devices and sensors and actuators. For example, the thermal dome model includes also a very detailed hydraulic model considering the pressure losses for the air distribution in the under construction of the thermal dome. Then we have a building model in combination with environmental climate data model that we can apply the approach for different locations in the world. Then we have openHAB with the help of the Modelica device driver library. All these signals are sent to our digital twin model, to openHAB, which controls the digital twin. And then, for example, openHAB compares the model state, this is the first model, the real model, with the digital twin of the same room, and then it can control the different devices, for example, to feed in cold or hot air into the thermal dome model. And finally, we have the connection to Unity, where the user can interact with the model, for example, opening a window, adapt a thermostat, or be present or absent. Also, the presence of the user is combined with heat emission or moisture emission of his or her body. Later, if we have our real test bed, then we have still the building model, because this is in real time parallel running to the test bed, but then it's connected with real devices. You can see it here. Different devices, a humidifier, a fan, a radiator, and air conditioning device, for example. What is going on with openHAB? We need openHAB because it's an event-based system. User interaction means event. User interaction triggers event. And so if somebody changes with the interaction in the Unity model, this signal is indirect sent over Modelica to openHAB, and then openHAB try to reproduce by comparing the testbed signals with the modeling signals, the simulated climate in the climate chamber. We are using the REST API of openHAB to communicate with Python scripts with openHAB. And then we have also the integration of the different devices with sensors over the serial bus with a lot of Arduinos and some Raspberries. Then we have implemented our overall strategy for controlling the devices with an openHAB. Here we are comparing signals from the room model on the test beds. And at the moment, we have a strongly simplified controlling algorithm. It's more or less two-point controller, a little bit extended two-point controller. We will also improve this in future. Okay, now I will show you a short case study where we compare the digital twin with the test bed. On the left side, you can see the adaptation of the set temperature for heating and cooling within the single space room by the user in the virtual reality environment. And then you can see the different reactions. How does the test bed can, or how in which quality the simulated temperature can be reproduced in the test bed. In the digital twin, it works better, yes, of course. In the reality, a little bit less. We can see here, for example, the weakness of the present used cooling technology. We are just in the situation that we have improved this weak point, but you can see here in which manner the digital twin can serve to improve our real test bed to show the weak points. Now, at the end, I will show you a very short video about the test bed in action. I hope you can see it, that you get an idea how the approach works in the reality. It's a very short video, only about 2 minutes. I think it should fit in my presentation. Now the user starting doing his interaction in the virtual world. This is a Modelica model which runs in real-time parallel, delivering the values for the climate chamber. Okay. Now I come to my summary and the outlook. First of all, the digital twin helped us and will help us also in future to realize a more precise, also cheaper. We can save a lot of money without building too early, more simulating with the digital twin and faster design of the real test bed. Also, we figured out some weak points of our experimental setup, and then we can improve it more with a higher degree of security in the right direction. And we can control or test our control algorithms in advance with a digital twin and can apply it afterwards for our real test bed. In the future, we have definitely to make some improvements, for example, for the system dynamics. The largest challenge is the fast dynamics. For example, if a user is changing the location from room A to room B, if room A is air conditioned and perhaps room B is in a free floating temperature state, then we have to have a very fast temperature change. And we want to consider other indoor climate parameters like solar irradiation, air velocity, and moisture. It's included, but not very considered in detail. We have to improve that feature too. Finally, we will come to the next step of our project, where we start to integrate the second important parameter for thermal sensation. This is the temperature of the surface, which embed us within a space. For this purpose, we are using PT elements. You can see our first experiments on the right side, where we are generating heat and cold. And so we will add within our thermal climate chamber an inner cylinder of thermal pixels. And for this purpose, we have also extend our Modelica model for a very detailed fluid factor calculation method. Okay, if we're interested in a discussion, perhaps we can meet us in what was the tool? We up or no? I forgot the tool name. The coffee break, or perhaps also you can ask me some questions after my presentation now.
Thank you,